What happens when our morning alarm starts ringing? The reactive systems within us activates our sleepy hand that quickly goes to stop it. It's not just natural but one of the most efficient and effective way to handle the changes happening around us. No wonder why, we can find it almost everywhere. We can find it in most of our daily activities, in many common gadgets like the ACs or the UPS. And in advanced complex applications like air defense systems that reacts to so many incoming signals and informs or activates a complex set of systems. Our favorite Google Map that constantly guides billions of users worldwide as they move. The high-speed trading systems. Those handle lots of transaction per second. Real-time data analysis like Twitter trend analysis. Analyzing millions of tweets from all over the world. Are few examples showcasing the efficiency, scalabilities and the capabilities of these systems. Having seen the reactive systems being almost everywhere, let's deep dive to figure out what makes these systems so special or, rather so universal. At its core, the reactive system or the reactive programming is an approach which is focused on reacting to the events or the data as it arrives with appropriate actions. The important clause to mark here is, as it arrives. We will discuss this in more detail in few slides. But this is the point that makes the reactive components highly efficient and scalable. The key features which make the reactive systems so special and highly popular are: these systems are very highly scalable, efficient, responsive, robust, and resilient, while using simpler components which are loosely coupled, modular and declarative. Sounds like common jargons, is not it? Well, then, let's see the how and why parts of it up next. To start with, let's look at the scalability and efficiency part of these systems. No doubt this is the most important feature that makes it an integral part of our complex modern applications dealing with high volume of data on a real-time basis. A quick question. As an individual, how can you work in the most efficient way? Simple answer is when you can focus on your work without having to wait on others, and, secondly, if you delegate something, you should not follow up but rather get notified when it's done. In technical terms, we call it as non-blocking mode of interactions. And this forms the basis of high scalability and optimal efficiency in the reactive systems. Be it an event or a time-consuming external task like an API call to fetch a product detail, or even a long-running external workflow like a taxi booking request which needs manual approval steps. The reactive components are never blocked, i.e., they never waste their time waiting on them. Thereby, they could always run at their optimal best. Let's look at them with some sample examples. Let's start with the events first, which is very straightforward. If we go back to our morning alarm example, do we have to wait for it? Or are we blocked awaiting it, just because it's going to ring sometime? Obviously not. We can always enjoy our sleep until the alarm rings. All our events are similar. They are non-blocking and we just need a handler around it. The handler will let us know when it occurs so that we can trigger an appropriate action. Until then we can keep working on our other tasks. But, how about the time-consuming external actions or even the long-running external workflows? How are they made non-blocking? Let's try to understand it with a simple example from our day-to-day life. Let's say you are at your home enjoying a movie with your family. Suddenly you decide to have a pizza party, getting it from a nearby restaurant. Now you are dependent on an external system, the restaurant, to complete some task. Here there are two options. 1. You yourself can go to the restaurant, wait there and come back with the pizza, or 2. Place an order so that pizza can be delivered for you. In the first scenario you will have to take out some time to complete the process. Obviously, it is going to block you from watching the movie with your family. This is an example of a synchronous approach where you are blocked for 20 to 30 minutes on an external task. Whereas in the second case, you can continue doing what you like and the delivery boy can notify you at your doorstep with the pizza ready. This is an example of a non-blocking approach. Since we have handed it over to someone else to do it for us in parallel when we focus on our other work, we call it as asynchronous. With this non-blocking asynchronous approach, we just placed a request and forgot about it. Whether the delivery process took 20 minutes or 30 minutes, we could utilize that time for working on the other things we have on our hand. Again, we collected the pizza when the delivery boy knocked on our door. So, what happened here? We got our pizza ready, without wasting any of our precious time. As we can see, the notification mechanism or the delivery boy plays a key role here. It's because of them, we could focus on our other work, until the pizza is ready for our action. If we relate it to the JavaScript world, the act of the delivery boy is usually done by A callback, a promise, and a wait in an async await block or an observable. They notify us when our dependent call has responded so that we can proceed with the further actions. Actually, we usually specify the next steps within their code blocks. As we have observed in our pizza party example. By using non-blocking asynchronous calls for the external tasks, we can ensure the components do not waste any time for the delays or inefficiency of its dependent components. The efficiency of each component is its own, i.e., each component can work at its optimal best. If we remember, we wasted zero time of our own on getting our pizza ready. Secondly, it also helps us clearly identify the components creating the bottlenecks and fix them by scaling them or with other appropriate solutions. Having seen the benefits of non-blocking asynchronous calls on time-consuming external actions, let's look at the cases of long-running workflows. Now let's look at the taxi booking service. This involves interaction of a customer with multiple taxi drivers. Each booking request needs a lengthy approval process involving manual intervention. Obviously, we cannot use asynchronous calls for such lengthy response cycle. How can we make such interactions smooth and non-blocking? A reactive system using message-driven approach help us here. Instead of direct calls, we will channelize all the communication through a message system. When the user initiates the search request, the request will be stored into a message system and into a queue, say, request queue. Each request is an event here. An application can keep reading the incoming stream of events from the request queue and send notification to the nearby taxi drivers. When a taxi driver accepts the request, a new message will go to the scheduled ride queue. Another application will keep reading the incoming stream of events from the scheduled ride queue and notify the customer with ride details. What do we see here? There are different systems interacting with each other. No one need to call anyone other than the central messaging system. No one need to wait as they would be notified when their turn comes. So, effectively we have broken down a complex workflow of interdependent systems into a set of simpler non-blocking steps using the events and notifications. Like the callbacks or a promise in non-blocking asynchronous calls. In the message-driven systems, the act of the delivery boy can be done by a combination of message system plus stream processor to capture and process the incoming events. Webhooks or WebSockets can be used to notify the remote systems for their action. On the client side, we may use observables to receive the notifications. Well, this is a sample approach to show how an event-driven system works. But there can be few variations as per our underlying system and framework. Another important aspect of the reactive systems is that these are highly responsive systems at its core. We use it heavily in our front-end design for responsive calculations, responsive sizing of screen components. But, in fact, we can utilize this feature in any area as we like as feedback control systems for rule-based monitoring and proactive handling. For example, we can use a reactive system to design auto-scaling mechanism that adds or removes new instances as the load changes. We can feed required input like memory utilization limits, response times, etc. and formulate a set of rules to work the input values. Depending on the outcome of these rules, we can decide on our scaling requirements. Similarly, we may feed system health data for system monitoring and auto-recovery. When a system is not responding to our health check request, we may like to restart or recreate that instance. Another very common example for this is the Google navigation system that we use on a daily basis. Just set the desired route in the Google navigation system. Then constantly feed our GPS location as we move, so that it can use those location events, along with the inbuilt alert rules and the set path, to constantly guide and alert us as we move. Coming to the next feature, we can build very robust and resilient systems using reactive design. Let's say we have an online shopping application. When an order is placed, this need to be processed by multiple systems for various purpose. The order has to go to the order fulfillment system for further processing. It has to go to a notification system for notifying the customer, and to analytics systems for various monitoring purpose. One way to design this system is to let the order capture service call these systems and pass on the required information. But the problem here is that 1. We are unnecessarily overloading the order capture service with the task to inform other systems, and 2. We are also creating additional dependencies. What if one of these systems goes down? We need to add failover handling mechanism to retry sending the information at a later point. We can better go with a message-driven system to get rid of all these hassles. 1. With a message-driven system, the order capture service only need to register the order into a messaging system. Let the messaging system and the consuming applications decide how they want to consume these registered orders. The advantage here is that even if the notification system, monitoring and analytics service and the order fulfillment service all go down, the order capture service can still continue capturing and registering the orders. This makes the system robust against multiple failures. Moreover, once these failed systems are brought back into action, they can read all orders captured into the messaging system and avoid any kind of losses. This makes the system resilient even against unavoidable failures. The beauty of the reactive systems is that the components can work together and interact smartly with each other, but they can remain completely independent. They need not have to call each other directly. This allows us to design reactive systems with loosely coupled components. The simplest example to understand this is the system at the traffic signal. We have the pedestrians, the cars, trucks, bikes, and the traffic police. These are all completely independent entities but work in synchronized or coordinated way just by responding to the same set of traffic signals. A very simple example that shows how to use the events or state changes to update multiple independent components. Just another example of loosely coupled systems which we have seen earlier. Because of loose coupling, the reactive systems are quite flexible to changes or upgrades. We can easily add new components or features without affecting the other components. For example, we have 3 consumers here for our incoming orders. We can easily add a new one without the order capture service knowing about it, because it does not call anyone directly other than the messaging system. A service like the notification service might be used by many systems. If it is upgraded to a new one, we need not have to change our messages that we send the central messaging system. And, since we just talk to the notification service through the messaging system, we are least affected during the upgrade. Loose coupling also makes the system modular. In reactive systems, the ability to break down the workflows and the ability to break down the features allows us to build them in a modular way. In taxi booking system, we have broken down a complex workflow of interactions into simple and independent steps. For example, to elaborate on the simple steps, the customer module sends the booking request to the central messaging system, but does not bother about how the taxi module or any other module will receive it. It's the consuming module along with the messaging system's responsibility. Similarly, the taxi module, when accepts the booking request, it just sends a message again to the central messaging system. It does not bother about how the customer module will receive it. Again, as we have seen in our other example of online shopping application, we can break down features of a system into simpler modules, which can smoothly interact but remain complete independent. Let's take another simple example of YouTube video player. It has few common functions like play, pause, forward, etc. And, also, has got so many configuration actions. Even though the video player provides a wide range of features, these features has been categorized into multiple modules and submodules. Each module has specific user event-driven actions. By drilling down and categorizing specific event-driven features, we can simplify and modularize the whole reactive system into simpler modules of events versus actions. For example, here we can have modules like settings and under that submodules like playback speed, subtitles, quality, each having their own smaller sets of event and actions. Coming to the declarative feature. A declarative language makes the underlying system easy to use and the interactions human readable. Let's look at this SQL query. Select asterisk from solar_system where type equals planet. This simple SQL statement smartly hides complexities of the underlying database query implementation. This HTML snippet hides complexities of the underlying browser implementation that displays a table inside a section. Just specify what you need and be least bothered about how will it be done. Makes our life easy, is not it? Coming back to the reactive systems, as we know, we can think of these systems as a structured collection of events and actions, which essentially means it's a collection of what happened versus what needs to be done. This, along with message-driven design, allows us to design the components with declarative interfaces. The APIs can use JSON or YAML with declarative syntax for interaction. For example, in the taxi booking service use case, we can use declarative syntax like book taxi with configurable parameters like booking type, rental hours, 10, taxi type, SUV, and so on as shown. As we can see, this request from our customer module is designed purely based on our business needs, in a human-readable and configurable manner. Based on this message, the backends can decide how they want to plan the implementation part of it. This makes the system simple and user-friendly, just like the SQL queries or an HTML snippet. In case of our video payer example, the syntax may differ depending on the underlying framework. But the reactive systems support a clean event-to-action mapping, making it readable and easy to maintain. Well, so many features, so many examples. But these are the important basics to explore the whole reactive world of fun and excitements. Let's have a quick recap of all we have discussed so far. You may also provide your queries or comments below to let me know if it was easy and useful. The reactive systems are highly scalable and efficient because all interactions can be designed as non-blocking. Events are non-blocking because of the event handlers which help us trigger our actions. And, for the time-taking actions or workflows, we can use non-blocking asynchronous approach as well as event-driven approach. The reactive systems are responsive by nature. It's heavily used on the front-end design for responsive actions. We can use it as a feedback control systems in any area as we like. For monitoring, optimization and failover handling purpose. Reactive system enables us to break down complex workflows into independent steps and break down complex features into simpler event versus actions, thus allowing us to build loosely coupled and modular applications. As we have seen in the online shopping application example, event-driven systems allow us to build robust systems that can withstand multiple failures. Again, since we can persist the incoming events, the consuming applications can continue their work even after a temporary breakdown. This makes these systems resilient. Reactive components can be designed to support declarative interactions using languages like JSON/YAML. And, also, with a clean and declarative event-to-action mapping. That's all in this video on key features of the reactive systems. Thanks for watching. Do leave your comments or queries in the comments section below. And please like and subscribe for more such videos coming in future.